Let's try to solve this problem here. A 1 meter long horizontal tube with both ends open, okay, so this is an open pipe question, produced a loud sound of frequency 850 Hz when the vibrating tuning fork is placed at one end of the tube. So if you would like to sketch a situation, it will involve an open pipe. So I usually sketch an open pipe with just 2 lines. So since it's open, I'll just leave it open. What happens is I place a vibrating fork on one end of the tube, and this vibrating fork has a frequency of 850 Hz. That's why inside this open pipe there's a sound of frequency 850 Hz being produced. Okay, this loud sound occurs at the fourth overtone. Okay, let's label everything down. This pipe here has a length of 1 meter, and right now it is in 4th overtone. Okay, every time we see the word overtone, right, we have to be more extremely careful. Okay, if we talk about harmonics, then let's say 3rd harmonic, then harmonic, the end value will just be equals to harmonic number. So if it's 3rd harmonic, n is equals to 3. If it's 5th harmonic, then then your n is equals to 5. If it's the 100th harmonic, then n will be 100. But overtone is different. Overtone means how many times you go over the fundamental tone. So for that, for open pipe, for closed pipe, you have to be more careful in deciding what is your value of n. So this is how I usually do it. If it's an overtone, I will check first. This is both end open, so this is an open pipe. Okay, for open pipe, we know that there is no need to split between odd harmonics or even harmonics. All harmonics are accessible, so you can have F1 followed by F2 followed by F3 followed by F4 followed by F5 followed by F6, so and so on. This is what we can see if it's an open pipe. Okay, so we know that the first frequency here is also known as the fundamental tone. Okay, so if you go over the fundamental tone once, then you go to the 1st overtone. Okay, then if you go over for a 2nd time, then that will be called as the 2nd overtone. Go over for the 3rd time, that will be the 3rd overtone. Go over for the 4th time, this will be your 4th overtone. Okay, so we see that we are asking for 4th overtone. 4th overtone, n will be equals to 5. Okay, so we have to be very clear, our n is equals to 5, even though the word says 4th overtone, but our harmonic number is 5. Okay, so now they ask us to sketch and label the standing waveform in the tube. So usually when they ask for sketching, I will first sketch this is for a tube, this is not for stretch string. Stretch string usually I will sketch an equilibrium line first, but if it's a tube, I will sketch the tube first. So tube is represented by 2 lines here. Because it's open at both ends, I will not close any end of the pipe, and I will label this pipe here has a length of L, and L in this situation here it's 1 meter. Okay, then I'll proceed to think about how the nodes and antinodes should be arranged. Okay, if I have an open pipe, these 2 ends here are open. Okay, they are not closed. So if my air particles is at these ends over here, these particles here should have plenty of space for the particles to vibrate, because it's not restricted by any wall over here. There's no wall over here as well. So the particles are freely vibrating at these places. So we can consider these ends here to be antinode, because the particles are free to vibrate. If there's a wall, let's say a closed end, then there's a wall, then your particle cannot vibrate freely at those places. Then those will be called as nodes. Okay, if you have a wall. But now it's open to vibrate, so we'll consider them as antinodes. So you have antinodes at one end, antinodes at another end. So the simplest way to construct a standing wave will be to put in a node in between the 2 antinodes. So this will be the fundamental tone, or the 1st harmonic. Okay, so this is what we can see. But now they ask for the 5th harmonic, or the 4th overtone. So we need to go one step higher again. Then you can do your antinote at both ends. Make it slightly complicated by inserting an antinote in between. So now note in between the antinote. So this will be your second harmonic. Okay, you can proceed to do your third harmonic, fourth harmonic, and fifth harmonic. So by the time you reach the fifth harmonic, you see that you have your antinote at the side as well. But how many notes do you put in between? 1, 2, 3, 4, 5. You put in 5 notes in between. Okay, so you have A and A and A and A and A and A. Okay, by the time you go to the fifth harmonics, you see a pattern that looks something like this. Okay, a shortcut way to do it is, if you notice that the first harmonic, there's one note inside. Okay, the second harmonic, there's 2 notes inside. So by logic, you know that when you reach the fifth harmonic, you should have 5 notes inside. So please check, you have 1, 2, 3, 4, 5 notes inside this pipe over here. So that's one way of thinking about it. Then you don't need to sketch it from n is equals to 1 to n is equals to 5. You can straight skip to n is equals to 5. Okay, so now what do? We sketch the waveform. We know that at antinote, you should be at the maximum amplitude. Note should be at equilibrium. Antinote, note, antinote, note, antinote, note, antinote, note, antinote. Okay, so if we sketch the waveform, it'll be something like this. What am I doing? Yeah, I mess up my dots. Note. Sorry. Note should be in the middle. Antinote, note, antinote. Sorry, my blunt. My blunder. Let's do it again. Antinote, note, antinote, note, antinote, note, antinote, note, antinote, note, antinote. Okay, something like this. Then you know that there's another, the flip side of it. Okay, so this will be your waveform for the fifth harmonic or the fourth overtone. Okay, you can remove all the irrelevant stuff. Because the first harmonic and second harmonic are irrelevant, I remove it. Then usually another thing that I do is I'll label that distance between note and note, or antinote and antinote. We know that the distance between them is lambda over 2. So this is the fifth harmonic. You can label it as lambda 5 over 2. That's fine as well. So this is another lambda 5 over 2. The fifth harmonic wavelength. Lambda 5 over 2, lambda 5 over 2, lambda 5 over 2. Okay, just to show that there are 5 lambda over 2 that can be fitted inside this pipe over here. Okay, so this is the complete diagram for the standing waveform in the tube. Next, the speed of sound in the tube. The speed of sound, well, V is equals to F lambda. But right now we are in the fifth harmonic, so we can write as F5 lambda 5. Okay, the speed of sound is what we want to calculate. The frequency is given to be 850 Hertz. But how do we find lambda? We know from just now that we can see that the length of the pipe here can be equated to 5 times of lambda over 2. 5 times of lambda over 2. So if you rearrange it, the lambda is equals to 2L over 5. So this can be substituted inside 2L over 5. So proceed with your substitution. 850 Hertz, 2 times of length 1 meter divided by 5. Then you'll find that the speed is equals to 340 meter per second, which is roughly right. Because if you are using atmospheric air, okay, in air, let's write it down, in air, your speed of your sound is usually around 330 to around 340 43. Usually people use this value for the speed of sound. Okay, but if they ask you to calculate it, then you calculate it to be around this range, then that means you are roughly there lah. Okay, so this is how you find the speed of sound in the tube. Next, calculate the new fundamental frequency if one end of the tube is closed. Okay, so new fundamental frequency, one end of the tube is closed. Right now, your tube should have the same length. Okay, your tube should have the same length. So if I sketch it, it will still be a similar tube. The length is still 1 meter. But what's different right now is that it's closed at one end. If it's closed at one end like this, we close out one of the end of the pipe. So we know that the particles over here are not free to move. There's a wall blocking. So this side here will be a node, whereas the other side will be an antinode because the particles here are free to move. So this is the most basic standing wave that we can create because there's no A and A sit together, there's no N and N sit together. This is one N, one A. So it's logical to have this kind of arrangement. This is the simplest standing wave that we can find, and this should correspond to the fundamental frequency. So how many wavelength is that? Okay, we know that the wave should look something like this because node in the middle, antinode will be at maximum. Okay, so we know that distance between N and N, let's say if we have N and N, then this will be lambda over 2. But now we have only N and A, so we know that this is half of lambda over 2, this is lambda over 4. But this is fundamental, so lambda 1. Okay, so this is how we should understand the situation right now. Okay, again, they ask for fundamental frequency. You will still use back V is equals to F lambda. Your V will still be the same speed as just now, which is 340. Sorry, 340. Why? Okay, let me write down. V sound depends, not just V sound, okay? Let's keep it general. V depends on medium. Okay, so if there's no change in medium, okay, if you're not replacing atmospheric air with helium gas, okay, you're not changing a medium, then there'll be no change in V. Okay, if you do nothing to the medium, you don't change the gas, you don't heat up the gas, you don't pressurize the gas, you don't do anything to the gas, okay, if it's still the same atmospheric air as just now, then technically your V should not change because you're doing nothing to the medium. Okay, that's why even though you change the tube to a closed-end tube, you're changing the tube, you're changing the pipe, you're not changing the air inside the pipe. So that's why you can still retain the same speed of the sound, which is 340 meter per second. Then the frequency is what you want to find. But now the wavelength, we need to find L is equals to how many times lambda over 4? It's only 1 time of lambda over 4. So you can find that lambda 1 here is equals to 4. Okay, you can write F1 lambda 1 because technically this is first harmonic. First harmonic is the same thing as fundamental frequency. Okay, so F1, so lambda 1 will be 4 times the length of the tube. So now we are left with substitution. F1, 4 times length of the tube, 1 meter. Okay, so just divide by 4. You get your fundamental frequency to be equals to 85 Hertz. Okay, so nothing too complicated here. If they ask for the speed, the frequency of the lambda, you can do it using V is equals to F lambda, but always find the lambda for the wavelength. What's the relationship with the length of the pipe? Find the relationship between the wavelength and the length of the pipe, then your the rest I think should be easy enough really. Okay, so this is how you solve a question regarding open and closed pipe.